Alright, hi everyone. Welcome to this video where we'll be continuing from 15.3 on how to extract metals from their ores all the way to the 15.4 where we learned about how to prevent rusting as well as the conditions for rusting. So before we continue with the video on the two new concepts, let's just do a quick recap on this particular question that was being given out in terms of the practice using 2011's O-level questions on metal reactivity series, right? So in this question here, there's three different setups whereby there are different metals with different types of metal ions, right? And we being mentioned over here that in experiment 1, the student actually see the changes happening to both the iron rod as well as the solution. This tells us that in experiment 1, there was a reaction that happened over here. Now, in terms of changes that happened over here, it was mentioned in class that in terms of changes, we look at it in two layers. One is to look at it in terms of any form of solid changes, in terms of appearance, a new solid forming, a deposit forming, etc. Second one, we also look at the solution. The solution change in color, and in order to do that well, we do need to know what exactly are the colors of the solutions, right? Why did the change happen? Now, this is a question comparing between metals as well as a different metal ions, and this must be about the concept of displacement, right? So just a quick recap, displacement would be a concept that touches on the comparison between reactivity between two different elements, right? So this is the part that we need to come out in terms of the explanation. Later we'll take a look at the answer key, okay? Next one, you're supposed to write an ionic equation for the reaction that happens in experiment 2, right? So experiment 2 is a reaction between zinc metal as well as iron 2 ions. Now, for those of you who still remember what was mentioned in class, you know that when you're constructing an ionic equation here, there's a way to do it a bit faster. That means is to focus on the displacement elements. Over here, we know that there's zinc, we know that there's iron 2, and these two are actually reacting together for another. So what will the equation look like? We will have zinc as a solid metal reacting with our iron 2 ions. Now, iron 2 ions in a solution form, this will be our aqueous state, right? So this is what it means when we say that in this ionic equation, right, the metal, zinc, actually reacted with the iron 2 plus ions in the aqueous state. And in this process, what do they form? The zinc is going to displace the iron 2. That means the iron 2 is going to come out as just iron solid. And the process, the zinc is now going to become the ion inside as a compound. So then you have zinc. When zinc is an ion, the charge is 2 plus, right? This is something you need to know from Sec 3. And then you have your aqueous state over here. So this will form the ionic equation for this particular experiment 2, right? Zinc reacting with iron 2, giving you iron plus zinc ions. So this is something that you need to familiarize yourself with, and this allows you to write the ionic equation very, very quickly to score the 2 marks. Part C, there's actually mentioning that actually on in all three experiments, there was a reaction that is being observed. Now, what does this tell us in terms of the experiment? It means that from experiment 1, if there is an observation of reaction, it means that iron, I'll just use the symbol, is actually more reactive than copper. In experiment 2, if there's a reaction, it means that zinc is more reactive than iron. In experiment 3, if there's a reaction, it tells us that X is more reactive than zinc. You'll notice that when you're looking at this chapter of reactivity series, as well as when you're looking at group 17, the reactions, it's always very useful to compare things in terms of their reactivity, right? So once you know their reactivity, then you can actually arrange them based on who is the most reactive, who's the least reactive. Okay, so that will help you to understand better before we go on to the last to the answer key later on. Part D, thermal stability. Now this was the one that was just reintroduced about thermal stability of the carbonates of metals. So just to recap, basically, more reactive the metal, they actually forms more thermally stable compounds, or in this case carbonate. This means that the very, very reactive metals, when they were to form a carbonate, the carbonate actually doesn't really break down when they're being heated. Okay, so that means potassium, when it forms potassium carbonate will be very, very stable. It doesn't decompose when it's being heated up, right? So what this student did was they want to investigate the thermal stability of the different carbonates. And what then they did was to heat up the metal carbonate and then bubble the gas given off through lime water. Now we know that any gas that goes in lime water, this must be a test for carbonate. Okay, so this student is trying to say that if I heat up the metal carbonate and let the carbon dioxide goes into the lime water, I can see whether the metal carbonate is actually stable or not. So in terms of the results that he should record, definitely he should be looking at how the carbon dioxide interacts with the lime water. So could be how long it took for lime water to form white precipitate, for example, right? And then how will this affect the results later on in terms of what to know what's going on. So let's take a look at the answers now. First, we just want to highlight again that we are looking at color in terms of the solid, in terms of the solution. That's for part A1. You already went through in class. Explanation wise, we're also looking at how whether the student is able to explain about more reactive and then to use the keyword displacing something from its solution. Right, this is something you need to work on and try to familiarize yourself with. Our equation, as I mentioned before, is shown over here. Okay, next, in terms of the reactivity series, right, we see over here that going from the least to the most, you have copper followed by iron, followed by zinc, followed by X, right? So that is one way to look at the reactivity series. And how do you explain it? Explanation is a bit tedious, but basically it's the same to compare that, okay, which one is more reactive, then you can displace something from the solution. Likewise, which one is more reactive, you can displace, you can displace something from the solution. And then, which one is more reactive, you can displace something from the solution. Right, so you can see that there's a certain style that we are actually trying to explain. And every explanation should be phrased in this manner. Compare a metal to another metal. Okay, don't write zinc is more reactive than a compound. Okay, that doesn't make sense. Right, then you're asked to deduce what could be metal X, right? Then you can think through what would be suitable ones based on the questions they are answering over here. Now, one very important point to point out over here is that if you look at the answer key here, now we don't really choose the very reactive metals. We know that potassium, sodium, all these things are super reactive, but we don't choose them because technically you wouldn't do such an experiment because it's not safe, right? And if it's not safe, means it's not viable, means it's not feasible, right? So when you choose a metal, you also don't choose something that is too ridiculously reactive, right? Then that defeats the whole purpose. Okay, so that is for until part C. Now we go to part D, right? As what I mentioned earlier, what the student can do is to actually measure the time taken for the white precipitate to start to come out. Remember, what he's trying to investigate is he's trying to say that if let's say I have the metal carbonate that's over here inside, he's gonna heat it up, and then in the process, based on what the question is saying here, he's going to bubble the gas into lime water. Okay, so when he bubbles into lime water, his observation must be based on the white PPT, the white precipitate that he's trying to form, right? So what can he do is he's only able to see how fast whether the white precipitate comes out very quickly. But to be very fair, this is not a very good method, right? Because how are you gonna see white precipitate forming how fast or slow? It's impossible to see from your eyes, right? So, but that being said, it's okay. The question already said that it's lime water. We just go with it. So how can you conclude? Basically, the longer the time taken, it will mean that the more stable the metal carbonate is. Why? That's because it means that the harder to decompose to form your CO2. Okay, so basically what the question is trying to say over here is that if I take a longer time to get a white precipitate, it means that it's harder for the metal carbonate to decompose. Therefore, it's harder to get the carbon dioxide. Right? So it's something that we need to be able to understand in the context of this question. Alright, so with this, right, basically what we're trying to say is that you learn about reactivity series now, and then you have learned about how the different reactions happen. You learn about displacement, then now you learn about, oh, actually this affects the stability of the metal carbonate. In the next part of this video itself, right, we're actually going to quickly cover about the whole idea of extracting metal from their ore, right? So we're just going to skip through this part and take a quick look at the next learning objective, which is to see how the extraction of metals looks like, right? So basically, the key focus for this part of the video is that we need to understand how to obtain metals from their ores based on their reactivity. Secondly, we need to learn about the different conditions that's required for corrosion or in the form of iron rusting to happen. And last but not least, to describe this method called sacrificial protection, we'll talk more about this in later as well. So in terms of how are metals extracted from their ores, right? So let's start first by watching a very short clip to have a sense of this concept of extraction of metals, right? Because I think if you want to understand about what it means.
As you may already know, the Earth's crust is made of rocks. If you look closely at a rock, you will see that there are many different bits. Some bits are dull, whereas other bits are rather shiny. The main idea here is that all these components occur naturally. In other words, they are not made in a factory or by a human being. A naturally occurring element or compound is known as a mineral. Ore is simply a rock containing a high percentage of a certain mineral. For example, hematite contains a high percentage of iron. The extraction of iron from hematite is done in a blast furnace. Malachite contains a high percentage of copper. Cinnabar contains a high percentage of mercury. We can think about an ore a bit like a chocolate chip cookie. We really want the chocolate. If there are more chocolate chips in the cookie, then the extraction process would be more economically beneficial. As more minerals, in this case, the chocolate can be obtained. If there are fewer chocolate chips, then the extraction process may not be as economically beneficial. For the most part, the minerals are oxides, carbonates, or sulfides of the metal of interest. Some ores of nonmetals include quartz, which contain a high percentage of silicon in the form of silicon dioxide. Limestone is also an ore. Can you remember what is found in a high percentage in limestone? Pause, think, and continue when ready. The answer is calcium carbonate. Limestone contains a high percentage of calcium, but calcium exists as calcium carbonate. The iron in hematite is mostly iron 3 oxide. The copper in malachite is mostly copper 2 carbonate. The mercury in cinnabar is primarily found as mercury 2 sulfide. The extraction process for each ore can vary, but the key idea here is that the mineral must be present in a high enough percentage, or else the process would not be very economically.
Alright, so as what has been shown in this video, right, we're going to talk a bit more about how extraction looks like, but we are not going to go into the whole nitty-gritty about different types of ores, what are the different types of metals inside. Generally, for this concept, right, what we need to understand is that most of the time, a lot of the metals are very reactive, which means that they actually exist as compounds in the natural world, right? So this kind of ores is something that we need to be able to do something to it before we can get them out as the metals that we want for the reactions. So only the very, very, very unreactive metals like silver and gold and sometimes copper, right, they can be found naturally uncombined. So for those of us here who play games, right, we know that sometimes you can dig for those minerals, right, from different kind of games that you play, be it Minecraft, etc., right. We know that in order to get the pure metal, sometimes there must be some form of processing involved. Then the processing is actually what we call extraction over here, right? But for some of the metals that's very, very unreactive, like gold, basically you just dig it up, you will get the gold and you can do some simple separation without using the chemical process, and you can still get the gold in the pure form. Because they are so unreactive that they actually cannot react with anything, right? So a quick one. So we know that in the States, right, there's this place called the Red Rock Canyon, right, whereby all the rocks and the canyons is super red. And I just want to let you know that it's because of the oxidation of iron. We do know that in our QA notes, right, Fe3 plus as a chemical, right, tends to give off a reddish brown kind of coloration. So we do know that transition metals also form colored compounds. So this is actually a case to show you that actually these iron ores actually are giving off the red color that you see over here. But how do we get the iron out? What's the method to choose? It goes back to the whole idea of reactivity series again. Now, the more reactive a metal is, right, the harder it is to extract them from the ore. if you think about this line, it's quite similar to what we've been talking about throughout this whole chapter. The more reactive a metal is, the more stable their compound is, right? The harder it is for it to extract, to react the whole thing. So there's two main methods to do. One is what we call reduction using carbon. One is what we call electrolysis. Between these two methods, electrolysis is more intense, it will be more expensive, so on and so forth, right? So reduction using carbon is a much cheaper method, faster in a way, right? And usually, what determines is that electrolysis is more intense, so it's for the more reactive metal. Because the more reactive metals have the more stable compound, right? If you are a very low reactivity metal, right? Actually, what it means is that your compound is also rather unstable, right? So it's very easy for the reaction to happen, right? So therefore, you can just use carbon for the reduction. So how does this look like? Those metals that is above carbon, if you recall, we have this please stop calling me a, then you have your careful zebra, right? So your C is over here. Now, please stop calling me a careful zebra. The purpose is to put a carbon there to help you realize that, hey, those that's above carbon, right? Actually, carbon cannot do anything to them. Right? This is actually something we have went through before. So how do we extract the metal out? We actually use electrolysis. So this is using electricity to break down the metals in order to get the pure metal. Okay, so to break down the compound. If those that's below carbon, now if it's below carbon, that means we can use carbon to reduce the metal oxide. So for example, if you have ZNO, I can actually add it with carbon, and I can form Zn coming out, and then my carbon dioxide will be the byproduct. Right, so this is actually how carbon actually extracts. Extract means to take out. Right, it takes out the zinc from the compound of zinc oxide. But of course, you also have metals that's super unreactive, like gold. That means they just exist as uncombined in the natural state. So there's no need to do anything to them, they will just be by itself. Okay, so how do we choose which method to use for extraction? It really depends on your reactivity series again, right? So long as you are very clear about your reactivity series, which is the please stop calling me, etc, 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 then you should be fine for most of the questions in this chapter. You just keep applying the same thing. Okay, so just one quick example, right? So just now in the video, it was mentioned about this thing called hematite, right? So hematite is actually the ore for iron, right? And the main chemical inside is actually iron 3 oxide, our Fe2O3, right? So how do we obtain hematite? How do we obtain iron out from the hematite? We actually reduce it using carbon, and this whole process takes place inside a blast furnace. Now, blast furnace is no longer in your syllabus, right? It's in the older batch of student syllabus. So you just need to know that there's this method called reduction by carbon. Okay, so that forms the end of the extraction process. Now, in terms of what we have went through so far, we actually mentioned that majority of the metals are actually found in existing in ores or in terms of their compounds. Metals that's higher up in the reactivity series have compounds that's harder to break down, and you need to use the method of electrolysis. But metals that is below carbon actually form compounds that can be extracted using reduction by carbon. Now, going on to the last part on the conditions for rusting. Now, rusting is not new to everyone. We know what is this, and we have seen it before, right, around you. Now, rusting is basically a corrosion process. I just want to highlight that corrosion is the name of the reaction. Rusting is just a simpler way to call it because the reddish brown thing that you see on the iron, right, the name of it is actually called rust. That's why we use the word rusting to describe the whole process. Okay, but to be more accurate, rust is a chemical, and it has a formula. It's a chemical name known as hydrated iron trioxide, and the formula is shown over here. So what happens is that in order for rusting to happen, the iron must have two very important ingredients with it. One is oxygen, and the other one is water. Only when these two are present, then they will actually form rust, which is what we call hydrated iron trioxide. So you see in this formula over here, you see this X here, right? This should remind you about something I learned in Sec 3, right? Because these are what we call hydrated compounds, okay? So this itself is what rusting means. For the other types of metals like magnesium, aluminum, copper, so on and so forth, right? We don't use the word rust because rust is only for iron 3 compounds. So we'll use the word corrosion to describe what can happen to them. Okay, so just keep that in mind. Now, What is needed for rusting and what speeds up rusting process?
We place nails in 4 test tubes. We add a little distilled water to the first test tube. We pour the water with some table salt into the second test tube. We add freshly boiled distilled water. It contains less dissolved gases from the air, and a little edible oil to the third test tube. The layer of oil will prevent the air in the test tube from dissolving in the water. We add calcium chloride, which will absorb the water vapor present in the air, to the fourth test tube. We seal the test tubes with stoppers and put the rack aside for a few days. If we examine the contents of the test tubes afterwards, we'll see certain changes. In the first and second test tubes, the nails were in contact with air and water, so they become covered in rust. However, no rust formed in the third and fourth test tubes. In the third test tube, the nail was in contact with water, but there was no access for air. In the fourth test tube, there was no water. It appears that air and water are needed for rusting to occur. Did adding salt have any effect on corrosion? Let us look once again. It turns out that the addition of salt accelerated the rusting. That is why the salt spread on streets in winter damages the bodies of cars.
Alright, so as you can see from the video itself, right, this is a good experiment over here actually shows you that both air and water is needed for rusting. A lot of times students just thought that with water, rust will happen, but without air, as you can see from some of the test tubes here, the reaction actually doesn't happen. Likewise, without water itself, just with air, the reaction also doesn't happen. But what's also interesting from this video is that it shows that actually sodium chloride, salt, is actually something that speeds up rusting. This is the reason why if you go to places like Changi Beach, East Coast Park, or Sentosa, you know that nearer to the beach, nearer to the water area, right, where there's a lot of seawater, that's where you usually see a lot of the rusting that happens from the ships, the boats, or the metal chains they see over there. Okay, so now that we mentioned that rusting is something that we are aware of in terms of iron, also just to add another point to link it back to something you have learned before is that acidic substance can also speed up the rusting process. So, how can we actually prevent rusting from happening? There's actually a total of 3 main methods in terms of prevention of rust. One is to use a protective layer. Now, what does a protective layer do? It's really about applying a layer of things around the metal, right, to prevent it from coming into contact with oxygen as well as water. It could be plastic, it could be oil, or it could be plating it for different type of metals, or putting a layer of paint over it. So those of you who cycle over here, you know that your bicycle, right, the gears and the chains have to be oiled regularly to prevent rust from happening. Secondly, instead of doing all the layering process, you also can use this idea of alloys, right? We learned about alloys at the start of the chapter on metallic bonding, that they are actually much more durable. And over here, we have this idea of stainless steel made of nickel as well as chromium. This will help the steel to become resistant to corrosion. But what's most interesting for this chapter is actually the idea of a sacrificial metal. Now, sacrificial metal or sacrificial protection is this logic about what if, in order to protect the iron, right, I put something that's more reactive next to it. What's the point? The point is to let that something actually go through the reaction to corrode preferentially in place of the iron. So in a way, that metal is being sacrificed to protect the iron. So one very common example is the use of zinc, right? So zinc is often used in big ships like cruise ships or huge boats, whereby they actually install it at the bottom of the ship hull, right? What will happen is that this zinc, so the ship will be made out of steel, etc., the base, but they'll put tiny blocks of zinc inside at the bottom facing in the water. What happens is that when there's a zinc over there, instead of the iron or the steel rusting, the zinc will actually go through a reaction. And that is what we mean by sacrificial protection. The zinc actually react and then become a new chemical, but in the process protecting the iron or the steel from the whole process, right? So this is what we call sacrificial protection, right? If you apply one whole layer of zinc, that's actually a term that we call galvanizing. Okay, so there's this term that is existing over here. Right, so in summary, in terms of prevention of rust, right, there's a lot of methods, but I just want to really highlight that the one that we are really interested in our syllabus over here is really about sacrificial protection, or one of the examples is what I call galvanizing. It's really about you applying your concept of reactivity series to figure out which is the method to use to protect the iron. Okay, so these are just some of the methods that we are seeing over here and how they are being chosen based on the different types that I was mentioning just now. Okay, so if not, I think with that, we'll come to the end of this video. Let's move on to the next task.